Hello, I'm Seema and welcome to part 2 of the chapter Organic Chemistry, Some Basic Principles and Techniques. We will today be doing the subtopic, the tetravalence of carbon. I told you in the previous video that carbon, the atomic number of carbon is 6 and its electronic configuration is 1s2, 2s2, 2px1 and 2py1. And I told you about the tetravalence, that according to octet rule, carbon has 4 electrons in its outermost shell, that is the second shell, and it needs 4 more electrons to complete its octet, and therefore it shows a valency of 4. I also told you that one of the electrons from the s orbital jumps up to the 2p orbital, which is empty, and when it jumps up we get 4 half-filled orbitals, that is of the second shell, that is 2s has 1 electron, 2px has 1 electron, 2py has 1 electron, and 2pz has 1 electron. Just before an atom is going to react to form a compound, it usually undergoes hybridization. And hybridization occurs so that the molecule that is formed has a symmetrical structure. You see, when bonds are being formed, nature always favors symmetry over asymmetry. It is the molecule that will be formed will be more balanced. Like, you know, when you have a magnet, the positive and the negative will be equal, they'll be balanced. In electricity also, in atoms, if you really see, the number of protons and electrons are equal, because a balance and a symmetry has to be maintained, and when that is so, it is easy to do the rest of the work. We must first begin with a little balance. So it's the same. There are 4 orbitals that are available to form bonding, but these 4 orbitals are not the same. The s orbital is spherical in nature, while the p orbital is a dumbbell in shape. Right? So just before the atom reacts, it undergoes this hybridization, in which the first step is that 1 electron jumps up from 2s to 2pz, and these 4 orbitals that are formed, they merge together and they redistribute their energies, and they result in the formation of 4 equivalent orbitals. When this happens, we say this is sp3 hybridization. Hybridization has occurred between these 4 orbitals, resulting in the formation of 4 sp3 hybrid orbitals. When we say sp3, it means 1 s orbital and 3 p orbitals. So in all there are 4 orbitals. The result will also be 4 orbitals, but there will be a redistribution of energy. The p orbitals which were long will become slightly shorter. The s orbital that was small will become slightly longer, and all 4 of them will have the same shape. So the sp3 hybrid orbital would have 1 lobe, and it will have a smaller lobe. The smaller lobe will be that of the s part, and the bigger lobe will be that of the p part. So in this way we'll get 4 equivalent hybrid orbitals. Now it's not necessary when hybridization occurs, it has to occur between all the orbitals that are available. Sometimes hybridization occurs between just s and one of the p's. So that hybridization would be called sp hybridized orbital. There will be 2 orbitals which would be hybridized. They would be equivalent, half s character, half p character, 50% s, 50% p. In sp3 you have 25% s and 75% is p. You can also have sp2. sp2 means 1 s orbital and 2 p orbitals. So you get 3 hybrid orbitals which are sp2 hybrid. You've studied all this in the 4th chapter. And I would encourage you to review the chapter a little, so that you, because I'm not going to cover this in details right now. This is just a little revision of what we had done there. So based on that are the shapes of the carbon compounds. So we have understood that carbon has a tetravalency, it has a valency of 4. It shows hybridization. As a result of whatever hybridization it has, the molecule has a certain structure, or rather we should say that depending on how many bonds it is going to form, in what manner it undergoes the hybridization in preparation to form that molecule, as a result of which the hybridization, the molecule has a certain structure. So the shapes of carbon compounds are the result of the hybridization that the carbon atom has undergone before it went into the formation of the compound. Methane is an example of an sp3 hybridized compound. So methane has one carbon and 4 hydrogens. It means the S and all the 3 p orbitals are involved in hybridization. You get 4 equivalent hybrid orbitals. In C2H4, that is ethene, there is a double bond between the 2 carbon atoms, and each carbon is undergoing sp2 hybridization. One s and 2 p orbitals, which means there are 3 hybrid orbitals. The 3 hybrid orbitals form bonds. Every carbon forms one bond with one hydrogen, one bond with the other hydrogen, and one bond with carbon. The 3 hybrid orbitals are used to form these single bonds. The unhybridized orbital results in the formation of the pi bond. Again, this is something that you have studied earlier. So go through the 4th chapter to understand this better. And the third type of hybridization would be the sp hybridization, as is seen in ethyne. In ethyne, it is C2H2. The carbon ethyne has only sp, one s, one p. So 50% is s, 50% is p. There are only 2 orbitals. The 2 orbitals, hybrid orbitals, are used to form bonds when each carbon has sp hybridized, is sp hybridized. So it forms 2 bonds, one with the other carbon and one with the hydrogen on the other side. And the other 2 bonds are actually the 2 unhybridized p orbitals. They overlap sideways and result in the formation of the pi bonds. And therefore, we have these pi bonds here. So based on this, how does it affect the structure of the compound? Let us understand these structures. The s orbital is spherical in shape. The p orbitals are dumbbells in shape. The px we say is along the x-axis, py we call it because it's along the y-axis, and pz is along the z-axis. So basically there are 3 of them which are along 3 axes, that is x, y and z-axis. So if this is, let us say, the plane, then if the s or px is in this direction, py is in this direction, then pz will be 1/2 lobe in front of the board and 1/2 lobe behind the board. So along the 3 axes, that is how we show it in 2 dimensions. Now if you look at the structure, once the 4 hybridized orbitals are formed in sp3 hybridized compound, that is in methane, the structure is like this. If you take 4 of these pens, let me imagine that each pen, the colored part, the cap, is the S part, and the P part, sp3, 25% is the S part and 75% is the P part. So you have the pen like this, I have it like this, I have it like this. It becomes a little difficult to hold it that way, but I'll hold it this way for you to understand how the structure is formed. Okay, so very difficult to show it this way. The S, now I want you to imagine that the caps are on the other side. I can't hold them with my hand in a way where the cap should be here and the rest of the portion should be here. The cap should be there and the rest of the portion should be here. So it forms a tetrahedral shape. Every sp3 hybrid orbital is symmetrical and the resultant molecule is symmetrical. Hold it in any direction, you'll get the same shape. Right? So you get a symmetrical molecule with 4 symmetrical bonds which have 25% of S character. The smaller lobe is smaller, is S character. Due to the S character you have one smaller lobe, and due to the P character you have one large lobe. And you get the tetrahedral shape, and that's the shape of an sp3 hybrid. Any compound that has sp3 hybridized carbon would have this shape, the tetrahedral shape around the carbon atom. If you had sp2 hybridization, as you have in the case of ethene, sp2, there is a hybridization between one s orbital and 2 p orbitals. So again, the s character is less and the p character is double of that, right? 1/3 is the s character and 2/3 is the p character. So the smaller lobe, if it is 1/3 out of 1/4, 1/3 is larger. So the S lobe, the smaller lobe, becomes slightly bigger. But now you have only 3 orbitals, sp3. So these 3 orbitals would form a bond. Now you saw, in order to form a symmetrical structure, we got a tetrahedral shape. What was the reason? Why did we get a tetrahedral shape in the molecule? Why did we not get a square? Because in 3 dimensions, imagine this to be a sphere. Okay, this is not a circle, it's a sphere. You are imagining a ball. Remember, although I'm drawing it in 2 dimensions as a circle, you're going to imagine a ball. On the top of the ball is one point, that is the angle, the tip of that orbital. This one is on that side going behind the board, and these 2 are coming in front of the board. Only this one bond is in the plane of the board. And in the sphere, one of these is going to the back and 2 of these are coming to the front, but all of them have the same angle. And the smaller lobes are obviously along the same line. Why is this happening? Because at these angles, so the tetrahedral angle is 109 degrees 28 minutes. At this angle, the repulsion between the electrons will be the minimum, because this is the maximum distance at which the orbitals can exist. And since all electrons are negatively charged, if each orbital occupies the maximum distance, that is the basic principle, all negative charges at maximum distance, that is when the repulsion would be the least. Because each of these is inviting another electron from the adjacent atom to form a bond with it. So they have to be away from each other so that they can bond or they can share that electron with the orbital of the adjacent atom. That is the reason why we have the tetrahedral shape of the sp3 hybridized carbon. In the case of sp2, now you have 3 hybrid orbitals. So these 3 hybrid orbitals, what they do, they occupy the 3 corners of a triangle. They occupy the 3, so you imagine this to be a triangle. Okay, they are occupying the 3 corners of a triangle. Similarly, this is also another sp2 hybridized carbon, so these 3 are also making a triangle, right, in the board. And these 2 triangles are in one plane. So the sp2 hybrid orbitals, they form a triangular planar structure. The 3 bonds are along the 3 corners of a triangle. When you have 3 points, the maximum distance that is possible would be in one plane. Because if you put them closer, if you decrease the angle by any degree, these 2 electrons are going to come closer. You don't want that. In order for 3 of them to be as far as possible, you make an equilateral triangle. So on the 3 corners of an equilateral triangle, you have the 3 bonds. So it forms a triangular planar shape. But let us understand the structure of this molecule. When you have sp2 hybridized carbon, one of the p orbitals has got a single electron and it has not participated in hybridization. Now what about this electron and this orbital? The 3 orbitals, that is these 3, are along the 3 corners of a triangle. But this one is perpendicular to this plane. Now in the diagram, I show you this one. The one here is the one that is perpendicular. Do you see this one? This is not in the triangle. You see, it is not in any of the corners of the triangle. The corners were the heads. So this orbital is the one that was unhybridized orbital, and it is perpendicular to the plane of the triangle. Now both of these carbons have got this pz orbital, which is not hybridized, and therefore it is perpendicular to this plane. So this triangle and the other carbon, which also forms a triangle, one of these orbitals, sp2 hybridized orbitals, overlaps and results in the formation of a bond. Now, like these are the one dumbbell here. So one of these overlaps and forms a bond. Similarly, these 2, this has one bond here, it forms a bond with the next atom here. It has one here, so it forms a bond with the next atom here. Similarly, this one forms a bond here, this one forms a bond here. But you have one orbital here which is like this, which is perpendicular. Actually, it is, if this is the plane, then this one is perpendicular to it. It means it is like this and this is like this, right? But in order to explain, let me show. So let us imagine that the two triangles that I showed you were along this plane. The two triangles are along this plane. And the p orbitals in both the carbons are perpendicular to this. In the center, they are perpendicular. So one triangle goes here, and they form a bond between them, and these two dumbbells are standing like this. If I hold it like this with one hand, maybe, yeah. Now the two dumbbells which are perpendicular to this plane of the molecule of the sp2 hybridized plane made by sp2 hybridized orbitals, the unhybridized orbitals, they fall perpendicular to it and they overlap sideways. Do you see? It is overlapping sideways. The overlap is not head on. It is not overlapping like this. It is overlapping on the side. And they overlap sideways and result in the formation of a pi bond. So a pi bond, the first bond that was formed was in the plane by these two sp2 hybridized orbitals by overhead overlapping on the head. But the p orbital, which was unhybridized, overlapped sideways and resulted in a pi bond above and below the plane of the molecule. So with this, I hope you understand how the structure is different. Now, in the case of sp3, the S character is the least. It was only 25%. Here, it has in sp2, the S character is medium. And in sp, the S and P character are 50% each. So here you would say the S character is 33.33%, and the other SP, the P character is also 33.3% for one of the P's and 33.3% for the other P. In SP, the S character is 50%. So we notice that in sp3, the S character is the least. It means the P character is more the P character, longer will be the orbital, because P orbital is longer and S orbital is smaller. So if the smaller character is less, it means the longer character is more. So sp3 hybrid orbital is the longest. sp hybrid would be a little shorter because it has more S character, and sp will be the shortest because it has 50% S character and 50% Y character. So on the whole, this orbital will be the smallest. These two orbitals will be the smallest. So let us now come to the third, that is the sp orbital. The example of an sp hybrid carbon compound, is ethyne. In this again, two orbitals, that is S and P, are hybridizing, and there are two unhybridized orbitals. So whenever you have only two points or two lines, let us say, what would be the angle at which they would be at maximum distance? 180 degrees, right? So if this is the nucleus, one sp orbital will be on this side and the other sp orbital will be on the other side. So the molecule that will be formed will be linear. This was triangular planar, but this is a linear bonding that will take place. So the hybridized orbitals are going to form linear bonds. The two carbons are combining with each other, and the other bond on the other side, which is at 180, is forming a bond with a hydrogen here. Similarly, this carbon is forming a single bond here, that is with the sp hybrid orbital, and the other one is forming a bond with hydrogen at 180 degrees. It's a linear molecule. But in this case, there are two unhybridized orbitals, the 2py and the 2pz. Just as we understood here that the unhybridized orbital is not in the plane, it is above or below. In this case, you'll have it is a line, so a linear molecule. So one of the orbitals, unhybridized orbitals, may be above and below, but the other may be along another angle, right? So you get the one that is above and below will overlap sideways, Any two orbitals that are parallel, if they overlap sideways, they would form a pi bond. So it overlaps sideways, therefore it forms one pi bond, and another one that is this way. The original molecule was linear, right? The next unhybridized bond was like this, so the second bond was formed like this, the pi bond. And the third was like this, so it overlapped on the side and formed the third bond. So there are three bonds formed between two carbon atoms. One of them is the sigma bond, that is the first bond formed by the sp hybridized orbital, but the other two are formed by the unhybridized p orbitals, which are called pi bonds. So that is what you see here in the molecule. This is one orbital, the one parallel to it will be this. So these two will overlap and they would form, these two would overlap the sideways one. And the other orbital is this way, this one and this one. So these two would overlap to form a third bond. And that would result in the formation of ethyne. So we find how the hybridization affects the structure of the molecule. There is one more thing that is very important to know. If you have sp3 hybridized molecule, let us say this is your sp3 hybridized molecule, right? And in sp3 hybridized molecule, if I move, let us say this is an atom attached to the molecule. If I move this side, this side of the molecule, nothing happens to the rest of the molecule. If I move this, rotate this, nothing happens to it because it's just a single bond, and around the nucleus of carbon atom, if I start rotating this bond, it does not affect it. But in the case of this molecule here, like here you would have 4 hydrogens. In sp3, this would be a hydrogen, this would be a hydrogen. So if you move this hydrogen, nothing happens to the sp3. There's no problem with its rotation. Nothing, it still remains the same. I may rotate it, but it is still the symmetrical structure. It is still tetrahedral. So nothing happens. It can be the atom here, if you rotate it, it is possible to rotate the atom. Similarly, if I want the entire sp3 hybrid carbon to rotate in comparison to the hydrogen, I can still do it. And nothing happens to the structure. But in the case of sp2, I have the plane in which I have 2 triangles, and I have these 2 bonds, one above, one lobe up and one lobe down. Now imagine this is as if you have a bond here, one bond is here, this one, and the second bond is formed by 2 lobes above and below it. So this is the one in the plane, and there are 2 bonds above and below it, right? Now if I want to rotate this molecule, imagine if I want to turn this, one of these carbons, if I want to turn the molecule, if I move both the carbons, the entire molecule moves around. But if I try to rotate one of these, the line on top, that is the bond on top and the bond below it, will not let me turn. I can only go up to a certain angle and then I'm restricted. I can't turn further. It stops my restriction. So you see, in the case of an sp2 hybrid orbital, the rotation of one of the atoms is restricted. In sp3, it was possible to rotate the other atom and the other part of the molecule. But here, when you have 3, that is, you have 2 of them, 2 bonds, where one is the sigma bond, the other is the 2 lobes, the p orbitals, the 2 lobes which are overlapping, resulting in an electron cloud above, electron cloud below, and the electron cloud in the middle, of course, is the first bond. So these 2 electron clouds are fixed. Therefore, when you start turning it, it does not let you rotate. So the molecule loses its flexibility. It loses its ability to rotate if it wants to. And if you had the sp hybrid, there are 2 of these. It means one bond is there, one lobe above, one lobe below, and one lobe behind and one lobe in front. Now there are 5 of them. Imagine, is it possible to rotate this? It will be such a rigid molecule. So an sp hybridized molecule, around the two carbons, if you want to rotate one of the carbons, it would be very difficult because it would lose its rotation simply because there are lobes, lobes of electron clouds above and below, in front and behind in the case of sp2, in the case of sp. And in the case of sp2, you have one basic angle, one basic bond, and then one lobe above it and one lobe below it, restricting the motion if you want to twist it. So let me just read this now. Hybridization influences the bond length. Yes, let me explain this also. I told you that in sp3 hybrid, the S character is the least. In sp2, it is medium, and in sp, it is the most. The more the S character, the shorter is the bond, because S orbital is small and p orbital is long. If you have more p, out of 4 orbitals, 3 were p, they are all contributing to the length. And the S is a small one, so its contribution is less. So the length of the sp3 hybrid orbital will be the most, the length of sp2 will be lesser than that, and the shortest bond would be sp. What property would this affect? How would it affect? How does bond length affect? Bond length, what does it even mean? The shorter the bond, the closer the electrons are to the nucleus. And the closer the electrons are to the nucleus, the more electronegative, the closer the chances the electron that is coming from the other atom has to be attracted by this nucleus. And the closer it can come to the nucleus, the more stable it will be. So we say it influences the bond length and it influences the bond enthalpy. The closer the electron is to the nucleus, the more difficult it becomes to remove it, because the more is the attraction. And therefore we say that the energy required to break this bond will be more than the energy required to break this bond, and the energy required to break this bond will be the least, because the electrons here are further away. And greater the S character, greater is the electronegativity. Why? Because the closer the electron can come to the nucleus, the more electronegative would that orbital be. Now I'm talking of the orbitals. It influences the bond length in the molecule, it influences the enthalpy on the whole because of the bond strength, and it affects the greater the S character, greater would be the electronegativity of that carbon. So now let us again understand some characteristic features of these pi bonds. For the formation of a pi bond, parallel orientation, I'm not talking of the first bond. The first bond is a sigma bond. It is formed by the head-on overlap. For a pi bond, that is the second bond to be formed, the overlap is of an unhybridized p orbital, and the two lobes of the p orbitals must overlap sideways. In order to overlap sideways, these should be parallel. Imagine if I had two p orbitals, one was an x and the other one x, let us say, is hybridized, and I have py and I have 2pz. One orbital is 2py and the other is 2pz. If they overlap, are they overlapping? No, because the overlap, the electron cloud is in the two lobes. So unless the electron clouds overlap this way, the pi bond will not be formed. For pi bonding, the unhybridized orbitals should fall parallelly to each other and they should be adjacent. It's not that this atom has a parallel one and then this one has an orbital this way and the third one has this way. They have to be close enough to overlap. So we say parallel orientation of adjacent p orbitals. They should be of two carbon atoms or two atoms which are adjacent next to each other, is necessary for the proper overlap. Now I've shown you the overlap by this. Thus, in CH2, all bonds should be in the plane. Now from this fact itself, that the hybridization took place, the structure would be such that there is minimum repulsion between the electrons, or there is maximum distance between the bonds. So for the possibility that these p orbitals should fall parallel, they should overlap sideways, it becomes a necessity that the three angles of the sp2 hybrid should be in a plane. Only if they are in a plane, then would the p orbital, the unhybridized p orbital, be perpendicular to it, and then both of them are perpendicular, both of them are at the same angle, and they're parallel. Only then would they overlap and form the second bond. So thus in CH2CH2, that is in ethene, all bonds should be in the plane. And the p orbitals forming pi bond should be perpendicular to this plane. The p orbitals should be perpendicular to this plane, and they should be parallel to each other. They should be perpendicular to the plane of the molecule, and they should be parallel to each other so that they can overlap sideways. Half of the lobe is up above the plane, and the other half, the lower lobes, are below the plane, and you have these two electron clouds forming the two clouds above and below the plane of the molecule. So the pi bond should be perpendicular to this plane, and they should be mutually parallel. Rotation of one of the CH2 fragment, rotation of one of these CH2 fragments with respect to the other interferes with maximum overlap of p orbitals. If you try to rotate the one of these, the overlap of p orbital will not take place. And since the overlap will be disturbed, this rotation would be restricted. It will not be allowed for one reason, that the p overlap would be disturbed. Secondly, it is the attraction between the two would be so much that it is somewhat like this. The movement is not possible. So rotation of one of the CH2 fragments with respect to the other interferes with maximum overlap of the p orbitals, and therefore such a rotation of C double bond C is restricted. The electron charge cloud is above and below the plane. I showed you how, resulting in pi electrons being easily available to attacking regions. Now, if you really see, in the plane, there are so many electrons of the three bonds this side, one bond between the two carbons, right? One bond between the two carbons if this is the plane, and these two bonds. There are three bonds for each carbon in the plane. But these two, the half a lobe up, half a lobe down, so this bond, the pi bond, is a little more scattered. The electrons in the pi bond are a little more scattered, and they are a little loose because they are not in the plane. So the electrons which are present in the pi bond are available for bonding. They become, since they are a little loose, these become the weak points in the molecule. So these are the electrons which would participate in bonding or in chemical reactions. So the electron charge cloud is above and below the plane, resulting in pi electrons being easily available to attacking regions. Therefore, pi bonds provide the reactive centers in the molecule. For alkenes and alkynes, it is these pi bonds which provide the electrons for reaction. So it is this part of the molecule which would react. However long the chain may be, usually the ene or the yne part, the two carbons having the double bond or the triple bond, that will be the site of reaction. So this was about tetravalence of carbon, the shapes of carbon atoms, and the characteristic features of pi bonds. With this, I would like to wind up today's video. If you found it helpful, give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.